Can drinking water kill you? Why rats, and sometimes even people, die for science? And why do we use the most dangerous toxin in the world to cure wrinkles? Answers to these and other questions in today's episode of The Curiosity Show. On January 12, 2007, Jennifer Strange, mother of three, took part in a radio contest. The contest was called Hold Your Wee for a Wee, and it asked participants to drink as much water as possible without peeing. The one able to hold the most water would win Nintendo Wii, a video console. Jennifer wanted to win the console for her kids, and within 3 hours she drank almost 2 gallons or 8 liters of water. She didn't win, she took second place, but the worst was yet to come. She started having terrible headaches, and a few hours later she was found dead in her house. She died of water intoxication. But what exactly happened? Our blood is full of dissolved ions, mainly sodium, potassium and chloride. When Jennifer drank so much water, large amounts of it was absorbed into her bloodstream. As a result, the blood was diluted and the concentration of ions decreased, most notably the concentration of sodium. Now there are fewer ions in the blood than in cells around, so blood is hypotonic compared to the cells, and nature doesn't like imbalance. So when this hypotonic blood contacts other cells, the water from the blood will travel to the cells to balance the concentration of ions. This process is called osmosis, and as a result, the cell swells and will eventually explode. It's especially dangerous in the brain, and that's exactly what happened in the case of Jennifer Strange. Her brain started to swell and eventually was damaged. Brain damage was the direct cause of her death. Jennifer simply overdosed on water, but we knew the importance of dosage ages before that. In the 16th century, Paracelsus, the father of toxicology, was one of the first to acknowledge the importance of dosing. He was a huge advocate of using chemistry in medicine, and he was successful using salts and other minerals to treat various diseases. It was quite a revolution of his times, and his opponents often claimed that his remedies were toxic and dangerous. In response, he said the famous sola dosis facit venenum, meaning only the dosage makes the poison. He clarified that all substances are toxic if applied in high enough dose, and as he used low dose, he could cure patients safely and effectively. Paracelsus figured out that the dosage is what determines whether something is a poison or a remedy, and even something harmless like water can kill you if used in high dose. And unfortunately, as we saw in the case of Jennifer, he was right. So how do you actually find the dose that is safe and won't kill you? Well, we tested. In order to determine the toxicity of a given substance, we use something called LD50. LD50 stands for an acute lethal dose of 50%, or median lethal dose. It is the dose required to kill 50% of the tested population in a short period of time. Usually we test toxicity on rats and mice. For example, if we wanted to find LD50 of caffeine, we would take a small population of rats or mice, usually 10 or 20 animals. Then we would give them a certain dosage of caffeine and observe what percentage of the population dies after some time, usually up to 2 weeks. Then we would repeat the tests with different doses. In the classical LD50 tests, usually 5 different doses are tested. The dosage that results in the death of 50% of the population is the lethal dose 50, or LD50. LD50 is expressed in milligrams per kilogram of body mass, and the lower it is, the lower the dosage necessary to kill half of the population. So basically, the lower the LD50, the more toxic a given substance is. Pure caffeine, for example, has an LD50 of 3 to 400 milligrams per kilogram. For comparison, 1 cup of coffee contains around 100 milligrams of caffeine. It means that an average person who weighed 60 kilograms would need to drink over 240 cups of coffee to exceed LD50 and possibly die. That's a lot of coffee, obviously, but if you used pure caffeine, only 24 grams could potentially kill you. LD50 of water is obviously much higher. Specifically, it's over 90,000 milligrams or 90 grams per kilogram. So the same 60 kilogram person would need to drink over 5.4 liters to exceed LD50 and possibly die. Unfortunately for Jennifer, she significantly exceeded that limit. But there are substances that are way easier to overdose. For example, drugs. Let's take cocaine. LD50 for cocaine is only 95 milligrams per kilogram, so around 6 grams could kill a human. You think that's a small amount? It's huge compared to the most dangerous toxin in the world, the botulinum toxin. Its LD50 is only 3 nanograms per kilogram, so 180 nanograms could kill you. 180 nanograms, it's like 10,000 less than a grain of salt. So why do we actually care about all of this LD50 mess? Well, it's very important when you are working on some new medication or some food additive. Without knowing these values, we don't really know what is healthy and safe and what can be toxic. It's crucial when we want to establish some regulation on transport and also first aid procedure in case of intoxication. Yet, the classical LD50 testing is not really perfect. While it's helpful, predicting human toxicity based on animal models might be very misleading. There are huge differences between the species and the toxicity of different substances between different animals. For example, chocolate, even though it's perfect for us humans, it's deadly for dogs. On the other hand, in 1993, Fialuridin, a potential drug against hepatitis B virus, was working great in animals. It was tested on models including mice, rats, and even primates. But when the drug was tested on humans, the results were completely different. 7 out of 24 participants experienced liver failure and required liver transplantation. 5 out of these 7 patients died after or even before the transplantation. It was all because of a single protein that was different between humans and the animal models. On top of that, the classical LD50 tests require a lot of animals, and that's why it's not really commonly used nowadays. There are some better alternatives. One of the alternatives is the up and down test. Here, only one animal is given a starting dose. This dose is predicted based on the toxicity of similar substances or previous studies. If the mouse dies, the next one is dosed at a lower concentration. If the mouse survives, the next one is dosed at a higher concentration. This method allows us to estimate the deadly dose relatively well, while still using significantly fewer animals. Okay, but let's go back to the strongest toxin in the world. The botulinum toxin is produced in nature by bacteria called Clostridium botulinum. The toxin inhibits the release of acetylcholine from axons to muscles. Acetylcholine is crucial for muscle contraction, and without it, muscles can't contract. So the toxin makes the muscles paralyzed. It's extremely dangerous because it also affects the respiratory muscles. So a person poisoned with this toxin cannot breathe and simply suffocates to death. You might wonder, how do we even get in contact with this toxin? Is it actually that dangerous for us? The bacteria producing the botulinum toxins are obligatory anaerobes, so oxygen is poisonous to them. The bacteria can be found mostly in the soil, so when you fall on the ground and your blood contacts the soil, you might get poisoned. Additionally, Clostridium botulinum can make spores, resistant cell-like structures able to survive harsh conditions. These spores can be sometimes found in honey, but usually they are not dangerous because they get destroyed by the acid in our stomach. However, infants below 1 year old do not produce enough acid, and the spores from the honey can become activated. Active cells can start producing the toxin and cause death. That's why you can never give honey to infants below 1 year old. No honey for babies. The bacteria can also develop in improperly refrigerated food, like sausages. Then it's dangerous for adults as well. But is the botulinum toxin all that bad? Remember, it's the dosage that makes the poison. As the toxin paralyzes, but also relaxes skeletal muscles, we widely use it in medicine. One of the uses is to treat wrinkles. In fact, another, more well-known name for the botulinum toxin is BOTOX. A very low dose of BOTOX can be used to paralyze some of the facial muscles, causing wrinkles. As a result, the muscle relaxes and the wrinkle flattens. We use BOTOX to relax many muscles that contract unnecessarily. For example, we can treat strabismus or the crossed eyes. In this condition, one of the muscles controlling the eye movement is contracting too much and causes misalignment of the eyes. Using BOTOX, we can relax the muscle and align the eyes correctly. Okay, that's it for today. Subscribe for more science and stay curious.